The Carroll dialogue again. This little debate shows the difficulty of trying to use logic and reasoning to defend themselves. At some point, you reach rock bottom, and there is no defense except loudly shouting, "I know I'm right." Once again, we are up against the issue which Lewis Carroll so sharply set forth in his dialogue. You can't go on defending your patterns of reasoning forever. There comes a point where faith takes over. A system of reasoning can be compared to an egg. An egg has a shell which protects its insides. If you want to ship an egg somewhere, though, you don't rely on the shell. You pack the egg in some sort of container, chosen according to how rough you expect the egg's voyage to be. To be extra careful, you may put the egg inside several nested boxes. However, no matter how many layers of boxes you pack your egg in, you can imagine some cataclysm which could break your egg. But that doesn't mean that you'll never risk transporting your egg. Similarly, one can never give an ultimate absolute proof that a proof in some system is correct. Of course, one can give a proof of a proof, or a proof of a proof of a proof, but the validity of the outermost system always remains an unproven assumption, accepted on faith. One can always imagine that some unsuspected subtlety will invalidate every single level of proof down to the bottom, and that the proven result will be seen not to be correct after all. But that doesn't mean that mathematicians and logicians are constantly worrying that the whole edifice of mathematics might be wrong. On the other hand, when unorthodox proofs are proposed, or extremely lengthy proofs, or proofs generated by computers, then people do stop to think a bit about what they really mean by that quasi-sacred word proven. An excellent exercise for you at this point would be to go back to the Carroll dialogue and code the various stages of the debate into our notation, beginning with the original bone of contention. Achilles. If you have left angle bracket, A, down angle bracket, or up angle bracket, B, right angle bracket, hoop, C, right angle bracket, you also have left angle bracket, A, up angle bracket, B, right angle bracket, then surely you have Z. Tortoise. Oh, you mean left angle bracket, left angle bracket, left angle bracket, left angle bracket, A, up angle bracket, B, right angle bracket, hoop, C, right angle bracket, up angle bracket, left angle bracket, A, up angle bracket, B, right angle bracket, hoop, Z, right angle bracket, don't you? Hint. Whatever Achilles considers a rule of inference, the tortoise immediately flattens into a mere string of the system. If you use only the letters A, B, and Z, you will get a recursive pattern of longer and longer strings. Shortcuts and derived rules. When carrying out derivations in the propositional calculus, one quickly invents various types of shortcut, which are not strictly part of the system. For instance, if the string left angle bracket Q down angle bracket tilde Q right angle bracket were needed at some point, and left angle bracket P down angle bracket tilde P right angle bracket had been derived earlier, many people would proceed as if left angle bracket Q down angle bracket tilde Q right angle bracket had been derived, since they know that its derivation is an exact parallel to that of left angle bracket P down angle bracket tilde P right angle bracket. The derived theorem is treated as a theorem schema, a mold for other theorems. This turns out to be a perfectly valid procedure, in that it always leads you to new theorems, but it is not a rule of the propositional calculus as we presented it. It is rather a derived rule. It is part of the knowledge which we have about the system, that this rule always keeps you within the space of theorems needs proof, of course, but such a proof is not like a derivation inside the system. It is a proof in the ordinary, intuitive sense. A chain of reasoning carried out in the I mode. The theory about the propositional calculus is a meta-theory, and results in it can be called meta-theorems, theorems about theorems. Incidentally, note the peculiar capitalization in the phrase theorems about theorems. It is a consequence of our convention. Meta-theorems are theorems, proven results, concerning theorems, derivable strings. In the propositional calculus, one could discover many other meta-theorems, or derived rules of inference. For instance, there is a second De Morgan's rule. Left angle bracket tilde x down angle bracket tilde y right angle bracket and tilde left angle bracket x up angle bracket y right angle bracket are interchangeable. If this were a rule of the system, it could speed up many derivations considerably. But if we prove that it is correct, isn't that good enough? Can't we use it just like a rule of inference from then on? There is no reason to doubt the correctness of this particular derived rule, but once you start admitting derived rules as part of your procedure in the propositional calculus, you have lost the formality of the system, since derived rules are derived informally, outside of the system. Now, formal systems were proposed as a way to exhibit every step of a proof explicitly, within one single rigid framework, so that any mathematician could check another's work mechanically. But if you are willing to step outside of that framework at the drop of a hat, you might as well never have created it at all. Therefore, there is a drawback to using such shortcuts. Formalizing higher levels. On the other hand, there is an alternative way out. Why not formalize the meta-theory too? That way, derived rules, meta-theorems, would be theorems of a larger formal system, and it would be legitimate to look for shortcuts and derive them as theorems. That is, theorems of the formalized meta-theory, which could then be used to speed up the derivations of theorems of the propositional calculus. This is an interesting idea, but as soon as it is suggested, one jumps ahead to think of meta-theories, meta-meta-theories, and so on. It is clear that no matter how many levels you formalize, someone will eventually want to make shortcuts in the top level. It might even be suggested that a theory of reasoning could be identical to its own meta-theory, if it were worked out carefully. Then it might seem all levels would collapse into one, and thinking about the system would be just one way of working in the system. But it is not that easy. Even if a system can think about itself, it still is not outside itself. You, outside the system, perceive it differently from the way it perceives itself. So there still is a meta-theory, a view from outside, even for a theory which can think about itself inside itself. We will find that there are theories which can think about themselves. In fact, we will soon see a system in which this happens completely accidentally, without our even intending it. And we will see what kinds of effects this produces. But for our study of the propositional calculus, we will stick with the simplest ideas, no mixing of levels. Fallacies can result if you fail to distinguish carefully between working in the system, the M mode, and thinking about the system, the I mode. For example, it might seem perfectly reasonable to assume that since left angle bracket p down angle bracket tilde p right angle bracket, whose semi-interpretation is either p or not p, is a theorem, either p or tilde p must be a theorem. But this is dead wrong. Neither one of the latter pair is a theorem. In general, it is a dangerous practice to assume that symbols can be slipped back and forth between different levels. Here, the language of the formal system and its meta-language, English. Reflections on the strengths and weaknesses of the system. You have now seen one example of a system with a purpose, to represent part of the architecture of logical thought. The concepts which this system handles are very few in number, and they are very simple, precise concepts. But the simplicity and precision of the propositional calculus are exactly the kinds of features which make it appealing to mathematicians. There are two reasons for this. One, it can be studied for its own properties, exactly as geometry studies simple, rigid shapes. Variants can be made on it, employing different symbols, rules of inference, axioms, or axiom schemata, and so on. Incidentally, the version of the propositional calculus here presented is related to one invented by G. Gensen in the early 1930s. There are other versions in which one rule of inference is used, detachment usually, and in which there are several axioms or axiom schemata. The study of ways to carry out propositional reasoning in elegant formal systems is an appealing branch of pure mathematics. 2. The propositional calculus can easily be extended to include other fundamental aspects of reasoning. Some of this will be shown in the next chapter, where the propositional calculus is incorporated lock, stock, and barrel into a much larger and deeper system in which a sophisticated number theoretical reasoning can be done. Proofs versus derivations. The propositional calculus is very much like reasoning in some ways, but one should not equate its rules with the rules of human thought. A proof is something informal, or in other words, a product of normal thought written in a human language for human consumption. All sorts of complex features of thought may be used in proofs, and though they may feel right, one may wonder if they can be defended logically. That is really what formalization is for. A derivation is an artificial counterpart of a proof, and its purpose is to reach the same goal but via a logical structure whose methods are not only all explicit but also very simple. If, and this is usually the case, it happens that a formal derivation is extremely lengthy compared with the corresponding natural proof, that is just too bad. It is the price one pays for making each step so simple. What often happens is that a derivation and a proof are simple in complementary senses of the word. The proof is simple in that each step sounds right, even though one may not know just why. The derivation is simple in that each of its myriad steps is considered so trivial that it is beyond reproach. And since the whole derivation consists of just of such trivial steps, it is supposedly error-free. Each type of simplicity, however, brings along a characteristic type of complexity. In the case of proofs, it is the complexity of the underlying system on which they rest, namely human language. And in the case of derivations, it is their astronomical size, which makes them almost impossible to grasp. Thus, the propositional calculus should be thought of as part of a general method for synthesizing artificial proof-like structures. It does not, however, have much flexibility or generality. It is intended only for use in connection with mathematical concepts, which are themselves quite rigid. As a rather interesting example of this, let us make a derivation in which a very peculiar string is taken as a premise in this fantasy, left angle bracket p, up angle bracket, tilde p, right angle bracket. At least its semi-interpretation is peculiar. The propositional calculus, however, does not think about semi-interpretations. It just manipulates strings typographically and typographically there is really nothing peculiar about this string. Here is a fantasy with this string as its premise. 1. Left square bracket, push. 2. Left angle bracket p, up angle bracket, tilde p, right angle bracket, premise. 3. P, separation. 4. Tilde p, separation. 5. Left angle bracket, left square bracket, push. 6. Tilde q, premise. 7. P, carry over line 3. 8. Tilde tilde p, double tilde. 9. Right square bracket, pop. 10. Left angle bracket, tilde q, hoop, tilde tilde p, right angle bracket, fantasy. 11. Left angle bracket, tilde p, hoop q, right angle bracket, contrapositive. 12. Q, detachment, lines 4, 11. 13. Right square bracket, pop. 14. Left angle bracket, p, up angle bracket, tilde p, right angle bracket, hoop q, right angle bracket, fantasy. Now this theorem has a very strange semi-interpretation. P and not P together imply Q. Since Q is interpretable by any statement, we can loosely take the theorem to say that from a contradiction, anything follows. Thus, in systems based on the propositional calculus, contradictions cannot be contained. They infect the whole system like an instantaneous global cancer. The handling of contradictions. This does not sound much like human thought. If you found a contradiction in your own thoughts, it's very unlikely that your whole mentality would break down. Instead, you would probably begin to question the beliefs or modes of reasoning which you felt had led to the contradictory thoughts. In other words, to the extent you could, you would step out of the systems inside you which you felt were responsible for the contradiction and try to repair them. One of the least likely things for you to do would be to throw up your arms and cry, "Well, I guess that shows I believe everything now." As a joke, yes, but not seriously. Indeed, contradiction is a major source of clarification and progress in all domains of life, and mathematics is no exception. When in times past, a contradiction in mathematics was found, mathematicians would immediately seek to pinpoint the system responsible for it, to jump out of it, to reason about it, and to amend it, rather than weakening mathematics. The discovery and repair of a contradiction would strengthen it. This might take time and a number of false starts, but in the end, it would yield fruit. For instance, in the Middle Ages, the value of the infinite series 1 minus 1 plus 1 minus 1 plus 1 minus and so on, was hotly disputed. It was proven to equal 0, 1, 1/2, and perhaps other values. Out of such controversial findings came a fuller, deeper theory about infinite series. A more relevant example is the contradiction right now confronting us, namely the discrepancy between the way we really think and the way the propositional calculus imitates us. This has been a source of discomfort for many logicians, and much creative effort has gone into trying to patch up the propositional calculus so that it would not act so stupidly and inflexibly. One attempt, put forth in the book Entailment by A.R. Anderson and N. Belknap, involves relevant implication, which tries to make the symbol for if-then reflect genuine causality, or at least connection of meanings. Consider the following theorems of the propositional calculus. Left angle bracket P hoop, left angle bracket Q hoop P, right angle bracket, right angle bracket. Left angle bracket P hoop, left angle bracket Q, down angle bracket, tilde Q, right angle bracket, right angle bracket. Left angle bracket P, up angle bracket, tilde P, right angle bracket, hoop Q, right angle bracket. Left angle bracket P, hoop Q, right angle bracket, down angle bracket, left angle bracket Q, hoop P, right angle bracket, right angle bracket. They, and many others like them, all show that there need be no relationship at all between the first and second clauses of an if-then statement for it to be provable within the propositional calculus. In protest, relevant implication puts certain restrictions on the context in which the rules of inference can be applied. Intuitively, it says that something can only be derived from something else if they have to do with each other. For example, line 10 in the derivation given above would not be allowed in such a system, and that would block the derivation of the string left angle bracket P, up angle bracket, tilde P, right angle bracket, hoop Q, right angle bracket. More radical attempts to abandon completely the quest for completeness or consistency and try to mimic human reasoning with all its inconsistencies. Such research no longer has as its goal to provide a solid underpinning for mathematics, but purely to study human thought processes. Despite its quirks, the propositional calculus has some features to recommend itself. If one embeds it into a larger system, as we will do next chapter, and if one is sure that the larger system contains no contradictions, and we will be, then the propositional calculus does all that one could hope. It provides valid propositional inferences, all that can be made. So if ever an incompleteness or an inconsistency is uncovered, one can be sure that it will be the fault of the larger system and not of its subsystem, which is the propositional calculus. Crab Cannon. Achilles and the tortoise happen upon each other in the park one day while strolling. "Good day, Mr. A." "Why, same to you." "So nice to run into you." That echoes my thoughts. "And it's a perfect day for a walk. I think I'll be walking home soon." "Oh, really? I guess there's nothing better for you than walking. Incidentally, you're looking in very fine fettle these days, I must say." "Thank you very much." "Not at all. Here, care for one of my cigars?" "Oh, oh, you are such a Philistine. In this area, the Dutch contributions are of markedly inferior taste, don't you think?" "I disagree. In this case, but speaking of taste, I finally saw that crab cannon by your favorite artist, MC Escher, in a gallery the other day, and I fully appreciate the beauty and ingenuity with which he made one single theme mesh it with itself going both backwards and forwards, but I am afraid I will always feel Bach is superior to Escher." "I don't know, but one thing for certain is that I don't worry about arguments of taste. De gustibus non est disputandum." "Tell me, what's it like to be your age? Is it true that one has no worries at all?" "To be precise, one has no frets." "Oh, well, it's all the same to me." "Fiddle, it makes a big difference, you know." "Say, don't you play the guitar?" "That's my good friend. He often plays, the fool. But I myself wouldn't touch a guitar with a 10-foot pole." Suddenly, the crab, appearing from out of nowhere, wanders up excitedly, pointing to a rather prominent black eye. "Hullo, hullo! What's up? What's new? You see this bump, this lump, given to me by a grump, ho. And on such a fine day, you see, I was just idly loafing about the park when up lumbers this giant fellow from Warsaw, a colossal bear of a man, playing a lute. He was 3 meters tall, if I'm a day. I mosey on up to the chap, reach skyward, and managed to tap him on the knee, saying, "Pardon me, sir, but you are polluting our park with your mazurkas." But wow, he had no sense of humor, not a bit, not a whit, and pow! He lets loose and belts me one smack in the eye. Were it in my nature, I would crab up a storm, but in the time-honored tradition of my species, I backed off. After all, when we walk forwards, we move backwards. It's in our genes, you know, turning round and round. That reminds me, I've always wondered, which came first, the crab or the gene? That is to say, which came last, the gene or the crab? I'm always turning things round and round, you know. It's in our genes, after all. When we walk backwards, we move forwards. Ah me, oh my, I must lope along on my merry way, so off I go on such a fine day. Sing ho for the life of a crab, ta-ta-ole. Ta-ta-ole. And he disappears as suddenly as he arrived. That's my good friend. He often plays the fool, but I myself wouldn't touch a 10-foot pole with a guitar. Say, don't you play the guitar? Fiddle, it makes a big difference, you know. Oh, well, it's all the same to me. To be precise, one has no frets. Tell me, what's it like to be your age? Is it true that one has no worries at all? I don't know, but one thing for certain is that I don't worry about arguments of taste. Disputandum non est de gustibus. Figure 43 shows a short section of one of the crab's genes, turning round and round, when the 2 DNA strands are unraveled and laid out side by side. They read 1, 2, 3, 4, 5, 6, 7, 8, 9 T's, C, G, 9 A's, so on, and then the other strings shows 9 A's, G, C, 9 T's. Is it reversed? Notice that they are the same, only one goes forwards while the other goes backwards. This is the defining property of the form called crab canon in music. It is reminiscent of, though a little different from, a palindrome, which is a sentence that reads the same backwards and forwards. In molecular biology, such segments of DNA are called palindromes, a slight misnomer since crab canon would be more accurate. Not only is this DNA segment crab canonical, but moreover its base sequence codes for the dialogue structure. Look carefully. Oh, that's funny. The T's are the tortoise, crab, and Achilles, but what is the G? Oh, it's like the narrator. The okay. Achilles. I disagree in this case, but speaking of taste, I finally heard that crab canon by your favorite composer, J.S. Bach, in a concert the other day, and I fully appreciate the beauty and ingenuity with which he made one single theme mesh with itself going both backwards and forwards, but I'm afraid I will always feel Escher is superior to Bach. Oh, you are such a Philistine. In this area, the Dutch contributions are of markedly inferior taste, don't you think? Not at all. Here, care for one of my cigars? Thank you very much. Incidentally, you're looking in very fine fettle these days, I must say. That was actually kind of clever. Oh, really? I guess there's nothing better for you than walking. And it's a perfect day for a walk. I think I'll be walking home soon. That echoes my thoughts. So nice to run into you. Why, same to you. Good day, Mr. T. Oh, I forgot to flip. Oh, that's weird. This one doesn't have, there's like an, so at the start of the chapter, it has this up here, and it's not in there in the ebook version, but it has the reverse at the end of the chapter as well. Chapter 8, Typographical Number Theory, the Crab Canon and Indirect Self-Reference. 3 examples of indirect self-reference are found in the Crab Canon. Achilles and the tortoise both describe artistic creations they know, and quite accidentally, those creations happen to have the same structure as the dialogue therein. Imagine my surprise when I, the author, noticed this. Also, the crab describes a biological structure, and that too has the same property. Of course, one could read the dialogue and understand it, and somehow fail to notice that it too has the form of a crab canon. This would be understanding it on one level, but not on another. To see the self-reference, one has to look at the form, as well as the content of the dialogue. Gödel's construction depends on describing the form, as well as the content, of strings of the formal system we shall define in this chapter, typographical number theory, TNT. The unexpected twist is that because of the subtle mapping which Gödel discovered, the form of strings can be described in the formal system itself. Let us acquaint ourselves with this strange system with the capacity for wrapping around what we want to be able to express in TNT. We'll begin by citing some typical sentences belonging to number theory. Then we will try to find a set of basic notions in terms of which all our sentences can be rephrased. Those notions will then be given individual symbols. Incidentally, it should be stated at the outset that the term number theory will refer only to properties of positive integers and 0 and sets of such integers. These numbers are called the natural numbers. Negative numbers play no role in this theory. Thus, the word number, when used, will mean exclusively a natural number, and it is vital for you to keep separate in your mind the formal system, TNT, and the rather ill-defined but comfortable old branch of mathematics that is number theory itself. This I shall call in. Some typical sentences of in number theory are 1. 5 is prime. 2. 2 is not a square. 3. 1729 is a sum of 2 cubes. 4. No sum of 2 positive cubes is itself a cube. 5. There are infinitely many prime numbers. 6. 6 is even. Now it may seem that we will need a symbol for each notion, such as prime or cube or positive, but those notions are really not primitive. Primeness, for instance, has to do with the factors which a number has, which in turn has to do with multiplication. Cubeness, as well, is defined in terms of multiplication. Let us rephrase the sentences, then in terms of what seem to be more elementary notions. 1. There do not exist numbers a and b, both greater than 1, such that 5 equals a times b. There does not exist a number b, such that b times b equals 2. There exist numbers b and c, such that b times b times b plus c times c equals 1729. For all numbers b and c greater than 0, there is no number a such that a times a times a equals b times b times b plus c times c. For each number a, there exists a number b greater than a, with the property that there do not exist numbers c and d both greater than 1 such that b equals c times d. 6. There exists a number e such that 2 times e equals 6. This analysis has gotten us a long ways towards the basic elements of the language of number theory. It is clear that a few phrases reappear over and over. For all numbers b, there exists a number b such that greater than, equals, times, plus, 0, 1, 2, and so on. Most of these will be granted individual symbols. An exception is greater than, which can be further reduced. In fact, the sentence a is greater than b becomes there exists a number c not equal to 0, such that a plus b plus c. Oh, sorry, I was confused. There exists a number c not equal to 0, such that a equals b plus c. We will not have numerals. We will not have a distinct symbol for each natural number. Instead, we will have a very simple, uniform way of giving a compound system to each natural number, very much as we did in the PQ system. Here is our notation for natural numbers. Go on. 0, O, 1, SO, 2, SSO, 3, SSSO. The symbol S has an interpretation, the successor of. Hence, the interpretation of SSO is literally the successor of the successor of 0. Strings of this form are called numerals. Variables and terms. Clearly, we need a way of referring to unspecified or variable numbers. For that, we will use the letters A, B, C, D, E. But 5 will not be enough. We need an unlimited supply of them, just as we had of atoms in the propositional calculus. We will use a similar method for making more variables, tacking on any number of primes. Note, of course the symbol apostrophe red prime is not to be confused with prime numbers. For instance, E, D prime, C prime prime, B prime 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 prime, A prime 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 prime. I said one too many. Are all variables. In a way, it is a luxury to use the first 5 letters of the alphabet when we could get away with just A and the prime. Later on, I will actually drop B, C, D, and E, which will result in a sort of austere version of T&T. Austere in the sense that it is a little harder to decipher complex formulas, but for now will be luxurious. Now, what about addition and multiplication? Very simple. We will use the ordinary symbols plus and minus, plus and dot. Oh, multiplication? Yeah, okay. Plus and times, we'll call it that. However, we will also introduce a parenthesizing requirement. We are now slowly slipping into the rules which define well-formed strings of T&T. To write B plus C and B times C, for instance, we use the strings B plus C, B times C. There is no laxness about such parentheses. Oh yeah, I didn't mention the parentheses. There's no laxness about such parentheses. To violate the condition is to produce a non-well-formed formula. Formula? I use the term instead of string because it is conventional to do so. A formula is no more and no less than a string of T&T. Incidentally, addition and multiplication are always to be thought of as binary operations. That is, they unite precisely 2 numbers, never 3 or more. Hence, if you wish to translate 1 plus 2 plus 3, you have to decide which of the following 2 expressions you want. I think from now on, because it takes too long, I'm not going to read the actual formulas and stuff because it takes too long, and you can pause. The next notion we'll symbolize is equals. That is very simple. We use the equal sign. The advantage of taking over the standard symbol used in non-formal number theory is obvious. Easy legibility. The disadvantage is very much like the disadvantage of using the words point and line in a formal treatment of geometry. Unless one is very conscious and careful, one may blur the distinction between the familiar meaning and the strictly rule-governed behavior of the formal symbol. In discussing geometry, I distinguish between the everyday word and the formal term by capitalizing the formal term. Thus, in elliptical geometry, a point was the union of 2 ordinary points. Here, there is no such distinction. Hence, mental effort is needed not to confuse a symbol with all of the associations it is laden with. As I said earlier, with reference to the PQ system, the string hyphen 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 is not the number 3, but it acts isomorphically to 3, at least in the context of additions. Similar remarks go for the string SSSO. Atoms and propositional symbols. All the symbols of the propositional calculus, except the numbers used in making atoms, P, Q, and R, will be used in T&T. And they retain their interpretations. The role of atoms will be played by strings, which, when interpreted, are statements of equality, such as SO equals SSO, or SO times SO equals SO. Now we have the equipment to do a fair amount of translation of simple sentences into the notation of TNT. 2 plus 3 equals 4. SSO plus SSSO equals SSSSO. If 1 equals 0, then 0 equals 1. 2 plus 2 is not equal to 3. The first of these strings is an atom. The rest are compound formulas. Warning: the and in the phrase 1 and 1 make 2 is just another word for plus and must be represented by plus and the requisite parentheses. Free variables and quantifiers. All the well-formed formulas above have the property that their interpretations are sentences which are either true or false. There are, however, well-formed formulas which do not have that property, such as this one, b plus SO equals SSO. Its interpretation is b plus 1 equals 2. Since b is unspecified, there is no way to assign a truth value to the statement. It is like an out-of-context statement with a pronoun, such as she is clumsy. It is neither true nor false. It is waiting for you to put it into a context. Because it is neither true nor false, such a formula is called open, and the variable b is called a free variable. One way of changing an open formula into a closed formula or sentence is by prefixing it with a quantifier. Either the phrase, there exists a number b such that, or the phrase, for all numbers b. In the first instance, you get the sentence, there exists a number b such that b plus 1 equals 2. Clearly this is true. In the second instance, you get the sentence, for all numbers b, b plus 1 equals 2. Clearly this is false. We now introduce the symbols for both of these quantifiers. These sentences are translated into TNT notation as follows. Upside down E for exists, upside down A for all. It is very important to note that these statements are no longer about unspecified numbers. The first one is an assertion of existence, and the second one is a universal assertion. They would mean the same thing, even if written with C instead of B. A variable which is under the dominion of a quantifier is called a quantified variable. The following two formulas illustrate the difference between free variables and quantified variables. B times B equals SSO is open. I forgot. What are we doing with... Tilde is if. If there exists a number b such that b times b equals SSO. Wait. Oh, man. Sorry. Is that right? That can't be right. Or would that be, there exists a number b such that b times b does not equal SSO? Is closed, a sentence of TNT. I think that's what it was. The first one expresses a property which might be possessed by some natural number. Of course, no natural number has that property, and that is precisely what is expressed by the second one. The first one expresses a property which might be possessed by some natural number. Of course, no natural number has that property, and that is precisely what is expressed by the second one. Okay. It is very crucial to understand this. Yeah, there is no such value, is what it was saying. And so that's right. That's the 2-1. Okay. It is very crucial to understand this difference between a string with a free variable, which expresses a property, and a string where the variable is quantified, which expresses a truth or falsity. The English translation of a formula with at least one free variable, an open formula, is called a predicate. It is a sentence without a subject, or a sentence whose subject is an out-of-context pronoun. For instance, is a sentence without a subject, would be an anomaly, runs backwards and forwards simultaneously. Improvised a 6-part fugue on demand. Are non-arithmetical predicates. They express properties which specific entities might or might not possess. One could as well stick on a dummy subject, such as so-and-so. A string with free variables is like a predicate with so-and-so as its subject. For instance, SO plus SO equals B. It's like saying 1 plus 1 equals so-and-so. This is a predicate in the variable B. It expresses a property which the number B might have. If one were to substitute various numerals for B, one would get a succession of formulas, most of which would express falsehoods. Here is another example of the difference between open formulas and sentences. For all numbers B, for all numbers C, B plus C equals C plus B. The above formula is a sentence representing, of course, the commutativity of addition. On the other hand, all numbers C, B plus C equals C plus B is an open formula. Since B is free, it expresses a property which the unspecified number B might or might not have, namely of commuting with all numbers C. Translating our sample sentences. This completes the vocabulary with which we will express all number theoretical statements. It takes considerable practice to get the hang of expressing complicated statements of n in this notation, and conversely of figuring out the meaning of well-formed formulas. For this reason, we return to the 6 sample sentences given at the beginning, and work out their translations into T&T. By the way, don't think that the translations given below are unique. Far from it. There are many, infinitely many ways to express each one. Let us begin with the last one. 6 is even. This we rephrased in terms of more primitive notions as there exists a number e such that 2 times e equals 6. This one is easy. Note the necessity of the quantifier. It simply would not do to write it without the quantifier. This string's interpretation is of course neither true nor false. It just expresses a property which the number e might have. It is curious that since we know multiplication is commutative, we might easily have written just swapping around E and SSO. Or, knowing that equality is a symmetrical relation, we might have chosen to write the sides of the equation in the opposite order. Now, these 3 translations of 6 is even are quite different strings, and it is by no means obvious that theoremhood of any one of them is tied to theoremhood of any of the others. Similarly, the fact that "-p-q" was a theorem had very little to do with the fact that its equivalent string "-p-q" was a theorem. The equivalence lies in our minds, since as humans we almost automatically think about interpretations, not structural properties of formulas. We can dispense with sentence 2 is not a square, almost immediately. However, once again we find an ambiguity. The first way of writing it says it is not the case that there exists a number b with the property that b square is 2, while the second way says for all numbers b it is not the case that b square is 2. Once again, to us they are conceptually equivalent, but to T&T they are different strings. Let us proceed to sentence 3. 1729 is the sum of 2 cubes. This one will involve 2 existential quantifiers, one after the other. There are alternatives galore. Reverse the order of the quantifiers, switch the sides of the equation, change the variables to d and e, reverse the addition, write the multiplications differently, etc., etc. However, I prefer the following two translations of the sentence. Oh my. Tricks of the trade. Now let us tackle the related sentence 4. No sum of 2 positive cubes is itself a cube. Suppose that we wished merely to state that 7 is not a sum of 2 positive cubes. The easiest way to do this is by negating the formula which asserts that 7 is a sum of 2 positive cubes. This will be just like the preceding sentence involving 1729, except that we have to add in the proviso of the cubes being positive. We have to add in the provision of the cubes being positive. We can do this with a trick. Prefix the variables with the symbol s. You see, we are cubing not b and c, but their successors, which must be positive, since the smallest value which either b or c can take on is 0. Hence, the right-hand side represents a sum of 2 positive cubes. Incidentally, notice that the phrase "there exist numbers b and c such that," when translated, does not involve the symbol up angle bracket, which stands for AND. That symbol is used for connecting entire well-formed strings, not for joining 2 quantifiers. Now that we have translated 7 is a sum of 2 positive cubes, we wish to negate it. That simply involves prefixing the whole thing by a single tilde. Note, you should not negate each quantifier, even though the desired phrase runs, "there do not exist numbers b and c such that." Thus we get. Now, our original goal was to assert this property not of the number 7, but of all cubes. Therefore, let us replace the numeral, that's 7, right, by the string a times a all times a, which is the translation of a cubed. At this stage, we are in possession of an open formula, since a is still free. This formula expresses a property which a number a might or might not have, and it is our purpose to assert that all numbers do have that property. That is simple, just prefix the whole thing with a universal quantifier. In austere T&T, we could use a instead of b and a, or a prime instead of b and a prime prime instead of c, and the formula would become this. What about sentence 1? 5 is prime. We had reworded it in this way. There do not exist numbers a and b, both greater than 1, such that 5 equals a times b. We can slightly modify it as follows. There do not exist numbers a and b such that 5 equals a plus 2 times b plus 2. This is another trick, since a and b are restricted to natural number values. This is an adequate way to say the same thing. Now b plus 2 could be translated into b plus SSO, but there is a shorter way to write it, namely SSB. Likewise, c plus 2 can be written SSC. Now our translation is extremely concise. Without the initial tilde, it would be an assertion that 2 natural numbers do exist, which, when augmented by 2, have a product equal to 5. With the tilde in front, that whole statement is denied, resulting in an assertion that 5 is prime. If we wanted to assert that d plus e plus 1 rather than 5 is prime, the most economical way would be to replace the numeral for 5 by the string d plus se. Once again, this is an open formula, one whose interpretation is neither a true nor a false sentence, but just an assertion about two unspecified numbers, d and e. Notice that the number represented by the string d plus se is necessarily greater than d, since one has added to d an unspecified but definitely positive amount. Therefore, if we existentially quantify over the variable e, we will have a formula which asserts that there exists a number which is greater than d and which is prime. Well, all we have to do now is to assert that this property actually obtains no matter what d is. The way to do that All we have to do now is to assert that this property actually obtains, no matter what d is. The way you do that is to universally quantify over the variable d. That's the translation of sentence 5. Translation puzzles for you. This completes the exercise of translating all 6 typical number theoretical sentences. However, it does not necessarily make you an expert in the notation of T&T. There are still some tricky issues to be mastered. The following 6 well-formed formulas will test your understanding of T&T notation. What do they mean? Which ones are true, under interpretation of course, and which ones are false? Hint: the way to tackle this exercise is to move leftwards. First, translate the atom. Next, figure out what adding a single quantifier or a tilde does. Then move leftwards, adding another quantifier or tilde, then move leftwards again and do the same. Second hint: either 4 of them are true and 2 are false, or 4 false and 2 are true. Okay, I'm going to move on. How to distinguish true from false. At this juncture, it is worthwhile pausing for breath and contemplating what it would mean to have a formal system that could sift out the true ones from the false ones. This system would treat all these strings, which to us look like statements, as designs having form but no content. And this system would be like a sieve through which could pass only designs with a special style, the style of truth. If you yourself have gone through the 6 formulas above and have separated the true from the false by thinking about meaning, you will appreciate the subtlety that any system would have that could do the same thing, but typographically. The boundary separating the set of true statements from the set of false statements, as written in the T&T notation, is anything but straight. It is a boundary with many treacherous curves, recall figure 18. A boundary of which mathematicians have delineated stretches here and there, working over hundreds of years. Just think what a coup it would be to have a typographical method which was guaranteed to place any formula on the right side of the border. The rules of well-formedness. It is useful to have a table of rules of formation for well-formed formulas. This is provided below. There are some preliminary stages, defining numerals, variables, and terms. Those 3 classes of strings are ingredients of well-formed formulas, but are not in themselves well-formed. The smallest well-formed formulas are the atoms. Then there are ways of compounding atoms. Many of these rules are recursive lengthening rules, in that they take as an input an item of a given class and produce a longer item of the same class. In this example, I use X and Y to stand for well-formed formulas, and S, T, and U to stand for other kinds of T&T strings. Needless to say, none of these 5 symbols is itself a symbol of T&T. Numerals. 0 is a numeral. A numeral preceded by S is also a numeral. Variables. A is a variable. If we're not being austere, so are B, C, D, and D. A variable followed by a prime is also a variable. Terms. All numerals and variables are terms. A term preceded by S is also a term. If S and T are terms, then so are S plus T and S times T. Terms may be divided into 2 categories: definite terms, which contain no variables, and indefinite terms, which do contain variables. The above rules tell how to make parts of a well-formed formula. The remaining rules tell how to make complete well-formed formulas. Atoms. If S and T are terms, then S equals T is an atom. If an atom contains a variable U, then U is free in it. Thus, there are 4 free variables in the last example. Negations. A well-formed formula preceded by a tilde is well-formed. The quantification status of a variable, which says whether a variable is free or quantified, does not change under negation. Compounds. If X and Y are well-formed formulas, and provided that no variable which is free in one is quantified in the other, then the following are all well-formed formulas. The quantification status of a variable doesn't change here. Quantifications. If U is a variable and X is a well-formed formula in which U is free, then the following strings are well-formed formulas. Open formulas contain at least one free variable. Closed formulas or sentences contain no free variables. This completes the table of rules of formation for the well-formed formulas of TNT. A few more translation exercises. And now a few practice exercises for you to test your understanding of the notation of TNT. Try to translate the first 4 of the following in sentences into TNT sentences, and the last one into an open well-formed formula. All natural numbers are equal to 4. There is no natural number which equals its own square. Different natural numbers have different successors. If 1 equals 0, then every number is odd. B is a power of 2. The last one you may find a little tricky, but it is nothing compared to this last one. B is a power of 10. Strangely, this one takes great cleverness to render in our notation. I would caution you to try it only if you are willing to spend hours and hours on it, and if you know quite a bit of number theory. No, dang. A non-typographical system. This concludes the exposition of the notation of TNT. However, we are still left with the problem of making TNT into the ambitious system which we have described. Success would justify the interpretations which we have given to the various symbols. Until we have done that, however, these particular interpretations are no more justified than the horse apple happy interpretations were for the PQ system symbols. Someone might suggest the following way of constructing TNT. 1. Do not have any rules of inference. Oh, I forgot this. It's been a while. Do not have any rules of inference. They are unnecessary because, 2. We take as axioms all true statements of number theory as written in TNT notation. What a simple prescription. Unfortunately, it is as empty as one's instantaneous reaction says it is. Part 2 is, of course, not a typographical description of strings. The whole purpose of TNT is to figure out if and how it is possible to characterize the true strings typographically. The 5 axioms and first rules of TNT. Thus, we will follow a more difficult route than the suggestion above. We will have axioms and rules of inference. Firstly, as was promised, all of the rules of the propositional calculus are taken over into TNT. Therefore, one theorem of TNT will be this one, which can be derived in the same way as... Oh, man. Alright. Before we give more rules, let us give the 5 axioms of TNT. Oh man. This just never ends. When do we get more to concepts again? Alright. I'm gonna not read those. those. In the austere versions, use A prime instead of B. All of them are very simple to understand. Axiom 1 states a special fact about the number 0. Axioms 2 and 3 are concerned with the nature of addition. Axioms 4 and 5 are concerned with the nature of multiplication, and in particular with its relation to addition. The 5 piano postulates. Piano. I don't know. By the way, the interpretation of Axiom 1, 0 is not the successor of any natural number, is one of the 5 famous properties of natural numbers, first explicitly recognized by the mathematician and logician Giuseppe Peano in 1889. In setting out his postulates, Peano was following the path of Euclid in this way. He made no attempt to formalize the principles of reasoning, but tried to give a small set of properties of natural numbers from which everything else could be derived by reasoning. Peano's attempt might thus be considered semi-formal. Peano's work had a significant influence, and thus it would be good to show Peano's 5 postulates. Since the notion of natural number is the one which Peano was attempting to define, we will not use the familiar term natural number, which is laden with connotation. We will replace it with the undefined term jin, a word which comes fresh and free of connotations to our mind. Then, Peano's 5 postulates place 5 restrictions on jins. There are 2 other undefined terms, genie and meta. I will let you figure out for yourself what usual concept each of them is supposed to represent. The 5 Peano postulates. Genie is a jin. That's 1. 2. Every jin has a meta, which is also a jin. 3. Genie is not the meta of any jin. 4. Different jins have different metas. 5. If genie has x, and each jin relays x to its meta, then all jins get x. In light of the lamps of the little harmonic labyrinth, we should name the set of all jins God. This harks back to a celebrated statement by the German mathematician and logician Leopold Kronecker, archenemy of George Cantor. God made the natural numbers, all the rest is the work of man. You may recognize Peano's 5th postulate as the principle of mathematical induction, another term for a hereditary argument. Peano hoped that his 5 restrictions on the concept genie, jin, and meta were so strong that if 2 different people formed images in their minds of the concepts, the 2 images would have completely isomorphic structures. For example, everybody's image would include an infinite number of distinct jins, and presumably everybody would agree that no jin coincides with its own meta, or its meta's meta, etc. Peano hoped to have pinned down the essence of natural numbers in his 5 postulates. Mathematicians generally grant that he succeeded, but that does not lessen the importance of the question. How is a true statement about natural numbers to be distinguished from a false one? And to answer this question, mathematicians turn to totally formal systems, such as T&T. However, you will see the influence of Peano in T&T because all of his postulates are incorporated in T&T in one way or another. New rules of T&T, specification and generalization. Now we come to the new rules of T&T. Many of these rules will allow us to reach in and change the internal structure of the atoms of T&T. In that sense, they deal with more microscopic properties of strings than the rules of the propositional calculus, which treat atoms as indivisible units. For example, it would be nice if we could extract the string wait, what? Oh, just basically that SO does not equal 0 from the first axiom. To do this, we would need a rule which permits us to drop a universal quantifier, and at the same time, to change the internal structure of the string, which remains, if we wish. Here is such a rule. Rule of specification. Suppose u is a variable which occurs inside the string x. If the string all numbers u, x is a theorem, then so is x. And so are any strings made from x by replacing u, wherever it occurs by one and the same term. Restriction. The term which replaces u must not contain any variable that is quantified in x. The rule of specification shows the desired string to be extracted from axiom 1. It is a one-step derivation. Notice that the rule of specification will allow some formulas which contain free variables, i.e. open formulas, to become theorems. For example, the following strings could also be derived from axiom 1 by specification. There is another rule, the rule of generalization, which allows us to put back the universal quantifier on theorems which contain variables that become free as a result of usage of specification. Acting on the lower string. For example, generalization would give all numbers C, for all numbers C, the number following C plus SSO does not equal 0. Generalization undoes the action of specification and vice versa. Usually, generalization is applied after several intermediate steps have transformed the open formula in various ways. Here is the exact statement of the rule. Rule of generalization. Suppose X is a theorem in which U, a variable, occurs free. Then, for all numbers U, X is a theorem. Restriction. No generalization is allowed in a fantasy on any variable which appeared free in the fantasy's premise. The need for restrictions on these two rules will shortly be demonstrated explicitly. Incidentally, this generalization is the same generalization as was mentioned in Chapter 2, in Euclid's proof about the infinitude of primes. Already, we can see how the symbol manipulating rules are starting to approximate the kind of reasoning which a mathematician uses. The essential quantifier. These past two rules told how to take off universal quantifiers and put them back on. The next two rules tell how to handle existential quantifiers. Rule of interchange. Suppose U is a variable. Then the strings for all numbers U. I'll be right back. Darn it. Oh man, there's so many. Yeah, I'm not going to read any of them at this point. You may notice that both these strings are perfectly natural renditions in T&T of the sentence, 0 is not the successor of any natural number. Therefore, it is good that they can be turned into each other with ease. The next rule is, if anything, even more intuitive. It corresponds to the very simple kind of inference we make when we go from 2 is prime to there exists a prime. The name of this rule is self-explanatory. Rule of existence. Suppose a term, which may contain variables as long as they are free, appears once or multiply in a theorem. Then any or several or all of the appearances of the term may be replaced by a variable which otherwise does not occur in the theorem, and the corresponding existential quantifier must be placed in front. Let us apply the rule to, as usual, axiom 1. You might now try to shunt symbols according to rules so far given to produce this theorem. Rules of equality and successorship. We have given rules for manipulating quantifiers, but so far, none for the symbols equals and s. We rectify that situation now. In what follows, r, s, lowercase s, and t all stand for arbitrary terms. Rules of equality. Symmetry. If R equals S is a theorem, then so is S equals R. Transitivity. If R equals S and S equals T are theorems, then so is R equals T. Rules of successorship. Add S. If R equals T is a theorem, then SR equals ST is a theorem. Drop S. If SR equals ST is a theorem, then R equals T is a theorem. Now we are equipped with rules that can give us a fantastic variety of theorems. For example, the following derivations yield theorems which are pretty fundamental. Illegal shortcuts. Now here is an interesting question. How can we make a derivation for the string 0 equals 0? It seems that the obvious route to go would be first to derive the string for all numbers a equals a, and then to use specification. So what about the following derivation of all numbers for all numbers a equals a? What is wrong with it? Can you fix it up? I gave this mini exercise to point out one simple fact, that one should not jump too fast in manipulating symbols such as equals, which are familiar. One must follow the rules, and not one's knowledge of the passive meanings of the symbols. Of course, this latter type of knowledge is invaluable in guiding the root of a derivation. Why specification and generalization are restricted. And now let us see why there are restrictions necessary on both specification and generalization. Here are two derivations. In each of them, one of the restrictions is violated. Look at the disastrous results they produce. The wrong generalization results. Yeah. Faulty specification. Here is a simple puzzle. Translate, if you have not already done so, Peano's fourth postulate into T&T notation, and then derive that string into a theorem, or derive that string as a theorem. Something is missing. Now, if you experiment around for a while with the rules and axioms of T&T so far presented, you will find that you can produce the following pyramidal family of theorems. A set of strings all cast from an identical mold, differing from one another only in that the numerals O, SO, SSO, and so on have been stuffed in. As a matter of fact, each of the theorems in this family can be derived from the one directly above it, in only a couple of lines. Thus it is a sort of cascade of theorems, each one triggering the next. These theorems are very reminiscent of the PQ theorems, where the middle and right-hand groups of hyphens grew simultaneously. Now there is one string which we can easily write down, and which summarizes the passive meaning of them all. Taken together, that universally quantified summarizing string is this. For all numbers a, 0 plus a equals a. Yet with the results so far given, this string eludes production. Try to produce it yourself if you don't believe me. You may think that we should immediately remedy this situation with the following proposed rule of all. If all the strings in a pyramidal family are theorems, then so is the universally quantified string which summarizes them. The problem with this rule is that it cannot be used in the im mode. Oh yeah, that's true. Only people who are thinking about the system can ever know that an infinite set of strings are all theorems. Thus, this is not a rule that can be stuck inside any formal system. W. Incomplete systems and undecidable strings. So we find ourselves in a strange situation in which we can typographically produce theorems about the addition of any specific numbers, but even such a simple string as the one above, which expresses a property of addition in general, is not a theorem. You might think that is not at all that strange. since we were in precisely that situation with the PQ system. However, the PQ system had no pretensions about what it ought to be able to do, and in fact, there was no way to express general statements about addition in its symbolism, let alone prove them. The equipment simply was not there, and it did not even occur to us to think that the system was defective. Here, however, the expressive capability is far stronger, and we have correspondingly higher expectations of TNT than of the PQ system. If the string above is not a theorem, then we will have good reason to consider TNT to be defective. As a matter of fact, there is a name for systems with this kind of defect. They are omega incomplete. The prefix omega comes from the fact that the totality of natural numbers is sometimes denoted by omega. Here is the exact definition. A system is omega incomplete if all the strings in a pyramidal family are theorems, but the universally quantified summarizing string is not a theorem. Incidentally, the negation of the above summarizing string for all numbers of a, 0 plus a is not equal to a, is also a non-theorem of TNT. This means that the original string is undecidable within the system. If one or the other were a theorem, then we would say that it was decidable. Although it may sound like a mystical term, there is nothing mystical about undecidability within a given system. It is only a sign that the system could be extended. For example, within absolute geometry, Euclid's fifth postulate is undecidable. It has to be added as an extra postulate of geometry to yield Euclidean geometry, or conversely, its negation can be added to yield non-Euclidean geometry. If you think back to geometry, you will remember why this curious thing happens. It is because the four postulates of absolute geometry simply do not pin down the meanings of the terms point and line, and there is room for different extensions of the notions. The points and lines of Euclidean geometry provide one kind of extension of the notions of point and line, the points and lines of non-Euclidean geometry another. However, using the pre-flavored words point and line tended for 2 millennia to make people believe that those words were necessarily univalent, capable of only one meaning, non-Euclidean TNT. We are now faced with a similar situation involving TNT. We have adopted a notation which prejudices us in certain ways. For instance, usage of the symbol plus tends to make us think that every theorem with a plus sign in it ought to say something known and familiar and sensible about the known and familiar operation we call addition. Therefore, it would run against the grain to propose adding the following sixth axiom. For all numbers a, 0 plus a is not equal to a. It doesn't jibe with what we know about addition. But it is one possible extension of TNT, as we have so far formulated TNT. The system which uses this as its sixth axiom is a consistent system, in the sense of not having two theorems of the form x and